Hello everybody, my name is Marta Gallego and I am postdoctoral researcher in the Department of Food Technology at Universitat Politècnica de València in Spain. And my talk today is about simulated oral processing and gastrointestinal digestion of mushroom purees with added proteins and hydrocolloids. As an introduction section, I would like to say that the increasing life expectancy of the world population and decreased mortality have led to a growing rate of an aging society in which the elderly represent an important segment of the global population. In fact, it's estimated that the number of people over 65 years of age will reach 16% in 2050. Elderly people can experience difficulties associated with safety and efficiency in feeding, chewing, or swallowing due to anatomical and physiological alterations developed during aging. In this regard, texture-modified foods are foods whose consistency has been changed to achieve a safe and efficient food intake. Purees and creams are a good option for the elderly since they have a higher viscosity than liquids, allowing the control of the volumes and avoiding the risk of choking. Moreover, the viscosity of these foods can be easily modified by the addition of hydrocolloids or thickeners. The importance of food oral processing not only comprises a safe intake, but also texture-modified foods should suit nutritional needs in terms of digestion and absorption of nutrients. Digestibility of nutrients can be modified due to changes in fat structure that might increase the risk of malnutrition. Furthermore, protein requirements are increasing the elderly for muscle mass maintenance. For that, the enrichment or fortification of foods by the addition of proteins is a good strategy. Interactions between the complex food matrix with added hydrocolloids and proteins can affect samples' behavior during oral processing and gastrointestinal digestion. So, the nature and charge of the thickener and the nature, size, and structure of the added proteins can lead to changes in composition and physicochemical characteristics of the samples and thus influence in their digestibility properties. This study aimed to evaluate the impact of the nature of the protein and hydrocolloid added to mushroom purees on their simulated oral processing and gastrointestinal digestion. For that, samples were enriched with intact protein or with whey protein hydrolysate, as well as modifying texture by adding modified starch, which has neutral charge, or carboxymethyl cellulose, which is an anionic thickener. Regarding materials and methods, preparation of samples included first making the mushroom puree. Then it was enriched with proteins up to 4 times the original content. It was tested with the Kendall method. Finally, hydrocolloids were added to reach an apparent viscosity values of close to 2000 millipascals per second, which was tested by the Rheological method. This table shows the contents of proteins and hydrocolloids added to obtain the different samples. The oral processing was evaluated by a simulated mastication assay, which was done in a rheometer by a combined skimming flow RCR4 test according to chunk type. The purees were subjected to 10 cycles of compression-decompression to mimic the motion of the tongue and palate during oral processing. The test was done in presence and absence of saliva. So in this method, step by step, we can see that firstly, the sample was loaded and when applicable, saliva was added. During the compression step, the maximum positive force was registered, which was taken as a measure of material consistency. The fixed gap step was related to the tongue sliding against the palate, and apparent shared viscosity values and 10 seconds minus 1 were obtained. During the decompression step, values of the maximum negative force were taken, indicating the material adhesiveness. Samples were also subjected to in vitro gastrointestinal digestion following the standardized InfoGest protocol. This process includes the oral, gastric, and intestinal phases that are simulated according to the indicated conditions. Briefly, the sample was mixed with amylase enzyme for 2 minutes in the oral phase. Then the oral bolus was mixed with pepsine and incubating for 2 hours under acidic conditions. And finally, at the intestinal phase, the gastric kind was mixed with bile and pancreatin for 2 hours. Digested samples were then characterized in terms of flow rheological properties and protein digestibility. Experimental data obtained from flow curves were fitted by the power law model, and the parameters of apparent viscosity, consistency index, and flow behavior index were obtained. The apparent viscosity values were measured at 10 seconds -1, as this rate was close to that physiologically reported. To evaluate if changes in rheological properties were due to the dilution effect of the sample resulting from the addition of digestive fluids, the test was also carried out in diluted samples, which were subjected to gastrointestinal conditions, but only urine water. To evaluate protein digestibility, the content of preamylose as a proteolysis index was evaluated using the TMBS method. Results of simulated oral processing were obtained in the absence and presence of saliva, and these figures represent the values of maximum force versus the number of cycles. As explained before, the maximum positive force and maximum negative force will be related respectively to the consistency and adhesiveness of the samples. In general, it was not observed a reduction in the values as the number of cycles increased, except for the sample with whey protein and CMC that saw a slight reduction from the first to the second cycle. These constant values along the cycles will be expected in pureed foods, in which the structure was broken during the grinding process rather than during the oral processing. With saliva, samples with CMC in red lines show the highest values of consistency and adhesiveness, and the samples with modified starch show the lowest values. In presence of saliva, a decrease in all the parameters was observed due to dilution effect, although the sample's behavior was similar. However, no significant differences in consistency and adhesiveness were found between the samples containing modified starch, independently of the protein nature, due to the action of salivary amylase by hydrolyzing starch. Similar results were obtained for the apparent viscosity values, which are related to the tongue sliding against the palate. With saliva, samples with modified starch presented viscosity differences during the first 2 cycles, but then their hydrolysis of starch during time led to similar values for both samples. However, samples with whey protein and CMC show the highest apparent viscosity, suggesting that this sample will be more miscible with saliva and for an homogeneous bolus that will be more easily swallowed. The addition of proteins and thickeners to the food matrix, as well as the action of gastrointestinal enzymes and the changes in ionic strength, pH, and volume at its digestion phase, can affect samples' conformation and rheological behavior during gastrointestinal digestion. This table shows the parameters obtained for the flow rheological curves during the oral, gastric, and intestinal phase of digested samples and diluted samples. All the samples presented a non-Newtonian shear thinning flow behavior with n values lower than 1. The apparent viscosity and consistency values decreased through the gastrointestinal process, but the values in the diluted samples were higher than those of digested samples. This could be attributed to the effect of gastrointestinal conditions on the loss of the structure and the stabilization of the food matrix, rather than the effect of sample dilution resulting from the addition of digestive fluids. In digested samples, the highest values of these parameters after the oral and gastric phases were found for the purées with CMC, and values at the gastric phase were similar to those of the diluted samples. This fact suggests that these samples will be the least affected by the amylase and pepsin enzymes, probably due to interactions between negatively charged polysaccharides as CMC and positively charged or hydrophilic amino acid proteins give place to aggregates or complexes that will limit enzyme accessibility and make the sample less susceptible to rupture. At the intestinal phase, no significant differences were found between digested samples, so the dilution effect will be the main factor in reducing viscosity and consistency at the end of the gastrointestinal digestion process. Changes in flow characteristics because of the action of proteins and thickeners to the food matrix can limit or modify the action of gastrointestinal enzymes and thus nutritional properties of samples. In other words, the protein digestibility will be affected by the composition, structural organization, and physicochemical characteristics of the samples resulting from the added proteins and hydrocolloids and their interactions with the food matrix. In this context, the protein digestibility of the samples was evaluated as the content of free amino groups during the in vitro process, and results were the following. Before digestion, and as expected, the highest values were found for samples containing the whey protein hydrolysates, and then no significant changes in the content of free amino groups were observed after the oral phase. But the action of pepsin enzyme at the gastric step led to an important increment of free amino groups in all the samples, with the highest values obtained again for samples with whey protein hydrolysates. After the intestinal phase, the action of enzymes such as trypsin and chymotrypsin by hydrolyzing proteins greatly increased the content of free amino groups in all the samples, except for that with whey protein hydrolysate and CMC. So the combination of anionic polysaccharides and protein hydrolysates will reduce the protein digestion rate at the end of the gastrointestinal digestion process. As conclusion, I would like to say that samples with CMC at thickener show the highest values of consistency and adhesiveness and viscosity values during oral processing, which would facilitate a safe swallowing process. The flow behavior of these samples was scarcely affected by the condition of simulated oral and gastric phases. Combination of CMC with hydrolysates as protein source will reduce the protein digestion rate at the end of the gastrointestinal digestion. Thus, the study of the interaction protein hydrocolloid food matrix can help to develop products with specific characteristics to meet the needs of a specific population such as the elderly. And thanks for your attention.